Hey everyone, so in this video we're going to be talking about the binomial distribution. So let's do a quick review of discrete random variables because the binomial distribution is a discrete distribution. So for random variable x, if the values x can take on are discrete, then we say x is a discrete random variable. And remember, we talked about probability mass functions, and those are just functions that give the probability that a discrete random variable is exactly equal to some value. So now let's talk about the binomial distribution itself. So a binomial experiment is an experiment where there's a known number of independent trials, so we're going to call this n. Each trial is either a success or a failure. So you can think of any type of binary outcome. The most common one is going to be heads versus tails. And then the probability of success is the same for each trial, and we're going to use p to denote this probability of success. So like I said before, the most famous example of a binomial experiment is flipping a coin multiple times and observing the number of heads or observing the number of tails. And a binomial random variable represents the total number of successes during a binomial experiment. So for the coin flipping example, if we wanted to define a success as getting tails, then the number of tails we observe in those n trials would represent our random variable x. And then the distribution from this binomial experiment is one of the most common and useful discrete probability distributions, and we're going to learn all about that. So now let's define the binomial distribution. So there are two parameters for a binomial distribution. And remember, when we were talking about the normal distribution, we had the same thing. We had a mean and we had a variance. With the binomial distribution, our parameters are going to be n and p. And remember, n represents the number of independent trials, so that could be number of coin flips or something. And p represents the probability of success on each trial. So for coin flips, p would equal to 0.5. Whether we're interested in heads or tails, it would be 0.5. So if x is a binomial random variable, then we use this notation here to say that. We say that x follows a binomial distribution with the parameters n and p. That's the way that's denoted. And if x followed a normal distribution, which we'll get into later, this would say x follows a normal distribution with mean and variance. So that's how we read that notation. So the probability mass function for a binomial distribution is this. And I know it looks pretty complicated, but it's actually really nice because we have this in functional form and we don't need to list it out in a table like we did with some of the other discrete distributions that we looked at in the previous videos. So we read this as n choose x, and I'll go over that in a minute, times p raised to the x times 1 minus p raised to the n minus x. And then n choose x, if you're not familiar, this is going to be n factorial over x factorial times n minus x factorial. And if you're not familiar with what a factorial is, it's just that number times each of the integers below it. So 4 factorial would be 4 times 3 times 2 times 1, which would be 24. All right, so where in the world does this formula even come from? Well, there are two main parts to this. The first part is the n choose x part of it. And this is just the number of ways to get x successes. So remember in the previous video, we had the example where we flipped a coin twice and we were observing the number of heads. We could have gotten 0 heads, we could have gotten 1 head, or we could have gotten 2 heads. But remember, there was only one way to get 0 heads, and there was one way to get 2 heads, but there were 2 ways to get 1 head. And n choose x helps us come up with the right number of ways to get a certain number of successes, and that's how we account for that. And then the probability of each outcome is accounted for by this. So remember, each of those distinct possibilities from our sample space had a certain probability, and this is the probability of getting that outcome. So this is the probability of the outcomes, and this is the number of ways to get those outcomes. So that's where this formula comes from. So I hope that makes a little bit more intuitive sense. So now let's look at an example. So if we flip a coin 4 times, n is going to be 4 because we're flipping it 4 times. And if we define a success as getting heads, then our probability of success, or p, is going to be 0.5. So then the probability of getting exactly 3 heads is going to be p of 3. So all we're doing is plugging this into the formula. So remember, the first part of the formula was n choose x. And we know that n is 4, and we know that x is going to be 3 in this case, because we're interested in the probability of getting exactly 3 heads. So this is going to be 4 choose 3. Now the next part of the formula is p to the x 1 minus p to the n minus x. So we figured out that p is 0.5 because that's the probability of getting heads on one coin flip. And we know x is 3, and then we have 1 minus 0.5 raised to the 4 minus 3. So that's where this all comes from. So if we break this down a little bit further, remember n choose x is the same thing as saying 4 factorial over 3 factorial times 4 minus 3 factorial. And then just like before, we're going to have 0.5 to the third, and then we're going to have 0.5 to the 1, which is just going to be 0.5. So taking care of this first piece, 4 factorial, remember, is just going to be 4 times 3 times 2 times 1, so that's 24. 3 factorial is going to be 3 times 2 times 1, which is 6, and then 4 minus 3, which is 1. 1 factorial is just going to be 1. So this is going to be 24 over 6 times 1. And then the rest of this, we have 0.5 to the third, which ends up being 0.125 times 0.5, because 0.5 to the 1 is 0.5. So now all we need to do is do the multiplication here. So 24 over 6 is going to be 4, and then 0.125 times 0.5 is going to be 0.0625. So if we do all of that, we end up with 0.25. And that's the probability of getting exactly 3 heads in 4 flips of a fair coin. Now, going a little bit further into the example we just did, when n is equal to 4, there are 16 possible outcomes of this experiment. And we could list them all out. We could list out heads, 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 tails, heads, heads, tails, heads. We could list them all out. And there would be 16 of them. And there's nothing stopping us from doing that. I mean, we could list out all of them, but once you start to increase n, then you start to run into some problems, because a lot of times n is going to be more than 4. And the example I have here is that when n is equal to 15, there are over 32,000 outcomes. And we don't have the time to list all of that out. And it's a lot easier when we have the binomial PMF available to us to be able to just plug it into the formula and we come out with the answer right away. So this is the reason why we have the binomial PMF in place. It makes things a lot quicker and easier for us. So now let's talk about cumulative binomial probabilities. So the binomial PMF gives us probabilities at one value of x, but it doesn't give us cumulative probabilities. So we could answer the question of what's the probability of getting three heads in four flips of a fair coin, but we can't answer the question of what's the probability of getting three or fewer heads in four flips of a fair coin. We would have to take it one by one. We'd have to do P of 0 plus P of 1 plus P of 2 plus P of 3. And that's pretty time consuming. We can't easily calculate that using the binomial PMF. So, what we usually have to resort to is what's called a cumulative binomial probabilities table. Or if you have access to computer software, you could plug it into there and it will calculate the probabilities for you. However, I'm going to be using the cumulative binomial probabilities table here because in most stats courses, you're not allowed to use computer software on like a test, for example. You're only allowed to use the table. So I'm going to use the table in these slides. But if you have any questions about how to use software to calculate these probabilities, I'd be more than happy to answer them. So when we use the table, we have to know what n is and we have to know what p is, the two parameters. And then the cumulative binomial probabilities table tells us what the probability of the random variable x being less than or equal to x is for any possible value of x, which is really nice because now we have quick access to these probabilities. And what this means is we can avoid using the PMF altogether as long as we're allowed to look it up on a table. So here are some examples of cumulative binomial probability tables. This first table up here is where n is equal to 5, and the one down here is where n is equal to 10. And all you really need to know, if you say, okay, well, n is 10, and then let's say p is equal to zero point 0.3, then the probability of 5 successes or less would be right here because we're in the column of zero point 0.3 in the n equals 10 table. So the probability of getting 5 successes or less would be 0.953. And it's that easy. So we're going to go over some examples of how to use these tables and more concrete examples. So suppose there's a quiz with 10 questions and each question has 4 multiple choice options. So if a student completely guesses at random, let's say they didn't study and they're like, I'm just going to randomly fill in the bubbles or circle the answers or whatever they need to do on this test, what's the probability that the student gets at most 5 questions correct? So there are 10 questions, and what's the probability that they get at most 5 questions correct if they're just guessing randomly? So first of all, we need to verify that this is even a binomial problem in the first place. So we have a known number of independent trials, and these are the questions on the test. And then the probability of a success is the same for each trial. Each of the questions has 4 multiple choice options. So the probability of getting it right is 1 over 4 for each question. So what we could do is we could let x be the number of correct questions, and then x would be a binomial random variable because it meets all the conditions of being a binomial experiment. So since there are 10 questions, n is going to be equal to 10. And then each question has 4 choices with 1 correct answer. So the probability of success is going to be 1 over 4, or 0.25. And what we're trying to figure out, remember, is the probability that the student gets at most 5 questions correct. And another way of saying that is the probability that the random variable x is less than or equal to 5, because x represents the number of correct questions on this quiz. So now we can go back to the table. We know n is equal to 10 because there are 10 questions on the test, and we determined since there's a 1 in 4 chance of getting a question correct, p is going to be equal to 0.25. And what we want is the probability that x is less than or equal to 5. So that's what this is right here. So that's 0.98. So the probability that the student gets at most 5 questions correct by randomly guessing on this quiz is going to be 0.98. And if we wanted to express this as a percentage, we could say that there is a 98% chance that the student will get at most 5 questions correct on this quiz. So the moral of the story is the student probably should have studied for this quiz. So in the previous example, what if we asked about the probability that the student gets exactly 5 questions correct? Now, the table only gives us cumulative probabilities, but we can still use it to find the probability that x is exactly equal to 5, as if we would if we were to use the PMF. So what we can do is we can use two different cumulative probabilities and subtract one from the other one. So what we do is we take this red piece, which was the probability that x is less than or equal to 5, and then subtract off this blue piece, which is the probability that x is less than or equal to 4, and what we'll be left with is just 5, the probability that x is equal to 5. And that's how we get this. So the probability that x is equal to 5 is this red piece minus this blue piece. And remember, we looked up the red piece on the table and we determined that that was 0.98. And then if we were to also look up the blue piece on the table, we would be left with 0.922. So the probability that the student would get exactly 5 questions correct by randomly guessing would be 0.058. So that's how we find those point-wise probabilities using the cumulative binomial probabilities table. So now what if we asked about the probability that the student gets at least 3 questions correct? So that means what we're looking for is the probability that x is greater than or equal to 3. Now remember, the table gives us the probability that x is less than or equal to something, so we're going to have to find a way to do this. But remember, the binomial PMF is a PMF, so all the probabilities add up to 1. So the probability of any possible value of x is going to be equal to 1. So this entire red piece here is going to be 1. And what we're interested in is the probability that x is greater than or equal to 3. So what we can do is take 1, which is this red piece, and subtract off this blue piece, which is the probability that x is less than 3. Or in other words, the probability that x is less than or equal to 2. And that's something we know how to look up on the table. So if we write this out, it would be the probability that x is greater than or equal to 3, which is what we're interested in. This would be this red piece, which is just 1, minus this blue piece, which was the probability that x was less than 3. And we determined that another way to write this is this, the probability that x is less than or equal to 2. And we want to write it this way because we know how to look this quantity up on the table. So if we were to go and look that up on the table, it would be 0.526. And remember, we're subtracting from 1, so what we're going to be left with is 0.474. So the probability that the student gets at least 3 questions correct on this quiz is 0.474. So once again, it's not looking very good for the student. Now, the last thing I want to talk about here is the mean and the variance of binomial random variables. Now remember, when we have a random variable, it's going to have a mean and it's going to have a variance. So remember, the mean, we called this the expectation of x, and the expectation of a binomial random variable is just going to be n times p. The variance of a binomial random variable is going to be n times p times 1 minus p. And then the standard deviation, as always, is just going to be the square root of the variance. So let's look at an example. So we're going to flip a fair coin 100 times, and we're going to observe the number of heads we see in those 100 flips. And we can let x be a random variable that represents the number of heads we see in those 100 flips. And then in that case, this would qualify as a binomial experiment. So we're going to have n equals 100 because we were flipping the coin 100 times, and p is going to be equal to 0.5 because the probability of success, or the probability of heads, is going to be 0.5. So our expectation is going to be n times p, so that's 100 times 0.5. And so we're going to get 50 for our expectation. So in other words, if we flip a coin 100 times, then we would expect to see 50 heads. And that should make sense. That's kind of intuitive, right? If you flip a coin 100 times, you would expect half of the flips to come up heads. And then the variance is going to be n times p times 1 minus p. So that's going to be 100 times 0.5 times 1 minus 0.5. So this is just going to be 100 times 0.5 times 0.5, and we're going to get 25 for our variance. And if we wanted the standard deviation, we would take the square root of the variance. And so we would just be taking the square root of 25, and that's just going to be 5. So this is going to represent how much our experiment varies. So if we flip a coin 100 times, we could come up with 46 heads. And then the next time we might come up with 53 heads. And on average, the distance away from the mean is going to be pretty close to 5 if we do this a bunch of times. So I hope that makes sense a little bit. So anyway, that's the end of this video. I hope this was helpful and enjoyable to you, and I will see you in the next video. Take care.